And I'm live. That is cool. Today is 26th of August 2025, Tuesday, and today we are going to delve into knapsack, and that is cool. There is a article. Shit. Okay, my bad. Not this thing. There is a article here on CPE algorithms. This thing here on knapsack problems, and we are going to go through the whole thing on dynamic programming knapsack. Yesterday we did introduction to dynamic programming. Today we are going to go through this whole knapsack article and yeah, comprehensively. The goal is going to be that after we have gone through this whole thing, we can write knapsack solving programs anywhere, anytime. We should be expert in this, or being expert takes time, but at least we have some comprehensive understanding so that if someone is talking about knapsack, we know what is being talked about. So that is going to be the goal with today's stream. And my windows are a bit messed up. Now it is cool. Yep. And one more thing before we begin. Yesterday I was watching a video on dynamic programming, and this I saw something amazing. Like, I don't know why I was unable to know this. Why didn't I know this till now? It is this. There is dynamic programming without, yes, there are double M. There is dynamic programming, and dynamic programming is is a framework for finding solutions to some problems, and those problems need to have a few things. One thing is that, okay, well, before that, let's see, there are two ways you can implement dynamic programming. One is using recurrence, w- recurrence with memoization, and this is also top down dynamic. And the other one is iteration with tabulation, ION, tabulation. And yeah, this can also be further divided into two things. So this thing, in this recurrence formula, and there is this iteration with tabulation. In recurrence, we use recursion as our main mode of moving through states, and memoization is the way that we store the data in those states. And the model is top down. That is, we begin with our target solution, the thing that we want, and we divide that into smaller sub problems, and we find solutions to those by dividing them into even smaller sub problems. For example, a classic Fibonacci sequence example. Fibonacci sequence of n equals f of n minus 1 plus f of n minus 2. If n is greater than 1, if n is greater than 2, if n is equal to 1 or 2, we return 1. This is a top-down approach because you begin with the target of finding this thing, f of n, and you are dividing this problem into smaller subproblems of f of n minus 1 and f of n minus 2. And since there is going to be a lot of similar subproblems in this recursion tree when you draw this out, therefore you do not want to solve the same subproblems again and again, we use a thing called memoization, which is when you solve a subproblem, you put its answer into some data structure in which you are storing all the answers, and before solving a subproblem, you check there if the answer is already there. If it is, then you do not solve this subproblem, and you take the answer from that data structure and return the thing. You do not recalculate the whole thing. and then there is iteration with tabulation, and this is bottom up. Yep, we can write bottom up because here to find something like f of n, if this is your target Fibonacci sequence, the nth number in the Fibonacci sequence, you begin constructing by constructing the whole Fibonacci sequence. First number is 1, then 1, then 2, then 3, 5, 8, and 13, and 21, and dot dot. So you begin with this thing, then you find 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 this thing, and you are going from bottom till your nth number. And when you get to your nth number, you return the thing. For this, you generally use a loop, generally a for or while loop, something like that. And you have a table in which you are storing the whole thing. A table could be two-dimensional, like a matrix, or a table could be a one-dimensional vector, anything. And that is cool. This thing is much faster. This is not very fast. This is easier to visualize, but this is not very easy to visualize. They have their pros and cons. And with that, we can begin our knapsack thing. But this distinction was very important. I didn't know that there are two types of dynamic programming like this. Recursion with memoization, which is top down. You begin from the top, you go down, and then iteration, bottom up. In iteration, you do not always have to do bottom up. This is optional, but yeah, you can start finding but yeah, no. And this is tabulation, since your table, the later values in your table depend on earlier values, you have to do bottom up in iteration tabulation method. That is cool. In recurrence, this is the mode of movement through states, and memoization is the way in which you store those states. And here iteration is the mode of movement, and tabulation is the way method through which you store those states. And that is cool. We can begin with knapsack, zero knapsack, and then there is complete knapsack, which is cool. Prerequisites. We have already read the article Introduction to Dynamic Programming. We will just begin with this. What is this? Charm bracelet. Consider the following example. This thing, charm bracelet, knapsack problem. There are n distinct items and a knapsack of capacity W. And we have n distinct items and a knapsack of capacity W. Capacity W. Each item has two attributes, weight Wi and value Vi. You have to select a subset of items to put into the knapsack such that the total weight does not exceed the capacity W and total value is maximized. That makes sense. Okay. In this example above, each object has only two possible states, taken or not taken, corresponding to binary 0 and 1. Thus, this type of problem is called 0-1 knapsack problem. Explanation. Okay, there is the explanation. So what this thing is that we have a knapsack, a purse, a sack in which has a certain weight capacity. This this bag cannot contain items whose collective weight is more than W. W is the maximum weight of the items this sack can hold collectively. And you have a bunch of items, right? You have a bunch of items, and each item has two things. It has a certain weight. It would be much better like this. It has a certain weight, Wi, let's call it, and a certain, let's say, value, Vi. Everything has a certain weight and a certain value. So what your target is to fill this sack in such a way so that the items that you choose do not, first of all, obviously, do not exceed the weight capacity of this knapsack, and second of all, the sum of their values is the greatest. That is the thing. And you can make an analogy and say you are a thief, like you legit are a thief, and you are in a store. You are stealing some stuff from a store, and in that store there are a bunch of items with certain weights, and they have certain values. Like a diamond ring has lower weight, but it has a lot of value. And something like a furniture big chair has a lot of weight, but not a lot of value. So you would prefer to take the ring, the diamond ring, instead of the chair. And I don't know why you would have a diamond ring and a chair being sold in the same shop. Somehow it is the case. So you would like to put the diamond ring into your bag and not the chair. Why would you even keep the chair in a bag? But that is your goal. You need to get the items with the most value, and you have a certain weight limit. You didn't go to gym. You cannot lift stuff more than this W weight. That is our goal. And how do you achieve this? That is what we are going to see here. I don't know. We will see here. In this example above, the input to the problem is the following. Weight of the WIth item. Weight of the ith item, WI represents the weight of the ith item, and the value of ith item, VI, and the total capacity of the knapsack, W. Yep, W is the total capacity. Let's Fij be the dynamic programming state. Yes, Fij dynamic programming state holding the maximum value the knapsack can carry with capacity J when only the first I items are considered. That is the table. And since we see that this function takes in two arguments, therefore the whole table in which all the values for this function are stored is two-dimensional. It can have different values depending on this I and depending on this J. So that is two dimensions. Assuming that all states of the first I minus J items have been processed, what are the options of the ith item? Options for the ith item would be maybe I take the ith item or I don't take the ith item. That is the thing. When it is not put into the stack, the remaining capacity remains unchanged and total weight does not change. Therefore, the maximum value in this case is this. When we are not choosing the ith item, the maximum value would be not choosing the ith item for that particular weight. When it is put into the stack, the remaining capacity decreases to Wi and the total weight increases by Vi. So the maximum value in this case would be Vi, the value of the current item, and J minus Wi. That would be the best possible case for J minus Wi weight. That makes sense. And when you are using the initial Fi minus 1 items, but when you are using the initial I minus 1 items, excluding this item, and the weight is J, the total weight minus Wi, total weight till now. From this, we can derive the dp transition equation. Either I take an item and J, weight J and Fi, or I don't, and I will take the maximum of the two. Further, as Fi is only dependent on Fi minus 1, we can remove the first dimension. Okay, this thing I heard yesterday also. I was looking at something, and this is further. Okay, so this much already is a bit much, and we would have to go to our Excalibur and discuss this thing till now. And till this point, we see that this thing depends on two variables. So the state would have to be two-dimensional. But here they are saying further as Fi is only dependent on fi minus 1. We can remove the first dimension. We obtain the rule as this. So, okay. Okay, so after we have discussed this thing would make more sense then. Okay, what does this whole thing mean? We understand the question. This is the question. We understand the question, and after that, there are a few things. We have to create a table. Yes, we have total weight is W and total number of items is, let's say, N, and there we can create a table. It seems like a two-dimensional table. And in this table, let's say we can represent the weights like this, horizontally, and vertically we can represent the number of items. So this thing will represent here I, and this thing here will represent J, and our function is f of ij. This will return the highest value when considering the first I items with the total weight capacity J. And let's have some actual example. Let's say our total number of items are 4, and our total weight capacity is 10. So we can begin with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we can, of course, divide this thing like this, which I guess using an actual line would be much better, like this. That is actually horrible. Yeah, this whole thing repeated. That was kind of spot on. Yep, yep, something like this. And we can divide this thing vertically in 4 parts. One, when we are considering only one item, or we should start with 0, I think. 0 when we are considering the first one item, when 2 items, when 3 items, and when we are considering all the 4 items. And we can divide this thing this way. Yep, yep, cool. So now let's fill this thing first manually, and then we will go how to compute this. When our target weight is 0 and we are not considering any elements, and also we need the weights. What are the weights themselves? What are the weights? Weights and their values. First weight, second weight, third weight, and fourth weight. We can take anything, I guess. And our total weight capacity is 10. Let's say first weight has the weight of 4 and value 10. Second weight has, this is weight and this is value. Second one has weight 5 and value also 5. Then the third one has weight, let's say 9 and value 20. Then the fourth one has weight 1 and the value 2. That seems cool. So when your weight capacity is 0 and you are not choosing any elements, when you are not choosing any elements, does not matter whatever your weight capacity is, your total value is going to be 0. The value you are going to get is always going to be 0. It makes sense because you are not choosing any elements. You do not have anything to put into your put into your stack. Even if you can put weights up till 10, but you do not have anything to put there. And we can see what the best answer would be. Yep. I guess if you take this weight third, and the fourth one, your total weight capacity is completed 9 plus 1, 10, and you get a sum of 22. That would be the best thing when you are considering all the weights and your weight capacity is 10. That would be the best thing. Now here, when your weight capacity is 0, no matter how many elements you have, you cannot put anything there. So your total value is always going to be 0. So these two rows and this row and this column seem unnecessary. I guess we do not have to start with 0 then. Now here, when my weight capacity is 1 and I am only considering the first element, which is 4, I cannot put it there. Therefore, my value is going to be 0. For 2 also, I cannot put an item of weight 4 into a sack of weight capacity 2. Same for 3, but for 4, I can put it there. Then the weight capacity, my value would be 10. And here also, it would remain 10 because I do not have anything to put there. So it will remain 10. 10 would be the best value all the way. Now here, when I am considering the first two items with weight 4 and 5, and my weight capacity is 1, I cannot put it. So 0, 0, 0. But now 4, if I put this fourth item here, then I have the option of putting 4 and 5. Then yeah, I think I would be able to put it. Then this becomes 10. And when 5, I would not use this fifth item because its value is 5. Instead, I could use this fourth item and get a value of 10. So that is what we are going to go with till when we can also add 5. That would be at 9. So till 9, everything is 10, and at 9, we can also add this thing. It becomes 15. Our value becomes 15. So that is cool. Then when we are considering the first three items, again, we cannot add anything till we get to a weight capacity of 4. Therefore, 0, 0, 0. And here we can add 4. So answer would be 10. Here again, 10, 10, 10, and 10. And now when we have a weight capacity of 9, we would rather put this single element with a value of 20 rather than putting these two elements with a combined value of 15, because 20 is greater than 15, so 20. And here also the same thing. Now here again the same, but now when our weight capacity is 1 and we are considering the whole thing, we can put this thing with a value of 2 always. Yep, so 2, 2, 2. And when when our weight capacity is 4, we would rather add this element with a value of 10. Yep. When it is 5, we can add this fourth element, this element with a weight of 4, and this element with a weight of 1, with a total combined value of 12. Here again, 12, 12, 12. And here we would like to put this element with a weight of 9 and a value of 20. So 20 here, and at the end 20. This element with a weight of 9 plus this element with a weight of 1, with a total combined value of 22. 22. And our answer is 22 in this knapsack. Okay, we did this manually, but we want our program to do this. And in the question, we saw that if we are anywhere in this thing, let's say we are here, and we want to find knapsack function when we have 3 items, and our weight capacity is 3. So we are considering the third item and our weight capacity is 3. When that is the case, if I choose this, I have two choices. Either I choose this thing or I do not choose this thing. And by third, it means the third element, not a element with a weight of 3. The weight here is 9. That is the weight here. The weight here is 9. So if I do not choose this thing, either I do choose 9 or I do not. If I do choose 9, then whatever weight capacity remains would be 3 minus 9. That is minus 6, which is a no-no. So we cannot choose 9 here when our weight capacity is 3. That is bad. If we do not choose 9, then it would be same as f whatever the last element was. It was the element with weight capacity 5 and with the element with the weight 5 and weight capacity 3. That would be the answer for this thing. 9, 3, which is this, which is 0. And let's go here for this thing, because here the answer changes from this to this. If we were here, or we can do this for here, because everything before this was 0 and here also we had 0. So when we have this, when our item has weight of 1 and our weight capacity is also 1. So either we do choose this element or we do not. If we do choose this element, then the answer would be f of not choosing this element. The element before this would be 3, whose weight was 9, 9, comma 0. Weight is 0 plus the value of this thing, which is 2 plus 2. This thing would be the answer if we do choose this element. And if we don't, then the answer would be f of 9 with the weight of 1. F of 9 with a weight capacity of 1. So what do we have here? F of 9 with a weight capacity of 0, which is this thing, it is 0. And we have plus 2 here. So 0 plus 2, that is 2. And this thing, f of 9, 1. This is 9th. This is 9. This third element has a weight of 9. So this would be the thing, which is also 0. So we have option of choosing 0 and 1. And here we would go with 2, because that is better than 0. That is knapsack. I think we should be able to actually write this now, which is cool. Let's see. So this is iteration. Like here I said iteration with tabulation. This is the table and we are going to iterate. We are going to iterate with these two possibilities. F of I, j. This is I. I, j would be equal to maximum of either we do choose this element or we do not. If we do choose this element, then the last element f of I minus 1 and the weight would be j minus w I, subtract the weight of the ith element plus the value of this ith element, this thing, comma, take the maximum of this value, comma, f of not choosing this element, which is I minus 1, and the weight remains same. Weight remains j. Find the maximum between this value and this value. And in both the conditions, we only want to know whatever the values were in the last row, which is, that is, to calculate all the values for this row, we only need to know the values in this upper row. That is cool. Maybe we would be able to optimize this into a linear thing. So let's go. DSA, DP, let's CD knapsack. We did wrote something yesterday in knapsack kind of problem, but now we are going to do full knapsack. Shit, and okay, we will use this example only, this thing, when our weight is this, and this will be called knapsack 01.cpp. Why 01? 01 because for every item we have a choice. Either we do take it, which is represented by 0, or we do not take it, which is represented by 1. Okay, we take it is represented by 1, and we do not take it is represented by 0. So 01 knapsack. And this thing will return a integer. Knapsack is the name of the function. It will take in a vector integer called, let's say it will take two of these vectors, vector integer, one for weight and one for values, and then integer for total capacity, and we have to include a few things. Vector using namespace std. Yep, here we go. And yep, now we have to initialize this table, this whole table, and this table is going to have whatever this capacity is, this many columns, and whatever the size of weights and value is, that many rows, that many plus one for this thing, and one for this empty thing here. We can call this vector of vector integer, and it will be called dp. Dp is the general publicly accepted thing. It will have the number of rows that it is going to have is weight dot size plus 1 vector int, and this thing is the number of columns is going to be capacity plus 1. And now we would like to iterate starting from this thing, starting from item number 1. So for int I, we can, yeah, items I start with 0, I less than weights dot size and I plus plus. For every weight, we are going to go, now I is the number of items. So for every I, we will go this way, then we will go to the next I, and we will go through all the columns for that particular I. That is cool. For int j equals, and we will start our iteration from this column, this thing, when our weight capacity is 1, because when weight capacity is 0, the maximum value is by default 0. J equals 1, j less than equal to capacity and j plus plus. And for every f of ij, if either I do choose this element or I do not choose this ith element, there are only two options. So if I do choose this element or I do not, it will be dij equals maximum of when I do choose this element. When I do choose this element, it will dpi minus 1 and j minus the weight of this element. But I need to know that this weight does not become negative if j, the current weight, minus weight of the ith element. If that is greater than equal to 0, only then we will consider this thing. Then dp of I, choosing the first I elements, and not really I, because I, we are starting I with, okay, we can skip this thing, I guess. Yep, can we skip this? Yes, we can skip this. We do not need this. We do not need this, so this thing can be 0. Yep, this thing can be 0 when we are considering the first element. This thing can be 0. Yep, I think nope, nope, we do need this because we need always need a row above. We always need a row above, and I do not want to just look up there and check. So yeah, we do need that. We do need that. Yep, dp of I plus 1. That is how we are indexing. dp of I plus 1 with the jth weight equals, if we can get the target weight, if the target weight is dp of I j minus weight of the ith element. Just that, and dp of I plus 1 j equals maximum of dp of I plus 1 j, comma, comma, when we are not using this element, it would be dp of I, and weight would also remain the same. I think that much is cool. That much is actually enough. And then we can return dp of using all of the elements, which is going to be weights dot size plus 1 for the capacity. Shit, was that this simple? Shit, it seems to be done. And we can initialize our vector of integers weights, which was 4, 5, 9, and 1. And our vector, okay, I messed up. I ignored the values thing. Value of 4, the item with the weight 4 is 10, the item with the weight 5 is 5, the item with the weight 9 is 20, and for 2, for 1, it is 2. And I messed up. When we are choosing the element, the value is going to increase plus value of ith element, right? And here we can see out answer equals knapsack when using weights, values, and our capacity is, let's say, 10. This is 0 in knapsack, and we have to include this thing. Include IO screen. Why do I have chrono? Yep. Is that beautiful? Yep, that seems like beautiful. And today is also contest, which is cool. CD where concepts DP knapsack blank plus plus knapsack not slash out. Let's see the supposed answer that we want. We would like to see 22 being outputted here. Let's see. It is a segmentation fault, which is bad. Segmentation fault is not right. 10. So we messed up at some point. At 3 plus 1 weight. Yep, I goes from 0. Yep, that is also correct. If j minus weight I is greater than equal to 0, only then do this thing, which should be correct. And value I. Yep. But there seems to be some mistake. We are creating our table here called dp weight size I plus 1 and capacity Dimensions are correct. We are we are using weight first as the first index and j as the second index, representing the current target weight. And yep, we are iterating through all the weights for a given item. That is also correct. Yep. Okay. Yes, shit. This thing. My bad. My bad. Now it should be correct. Answer is 22. Shit, we just did knapsack. God of Beast, your messages are somehow retracted. I don't know. Like this thing happens at times. I don't know why this happens. Somehow this is bad. Okay, so this is cool. This is cool. We got this. This is now working. And let's see. We can maybe go to lead code knapsack. What is this? Is this hard? Tallest billboard, two key keyboard, profitable schemes. I would like to shopping offers. I would like to test this thing on some actual data. In lead code store, there are n items to sell. Each item has a price. However, there are some special offers, and a special offer consists of one or more different kinds of items with a sale price. You are given an integer array price, where price I is the price of the ith item, and an integer array needs, where needs I is the number of pieces of the ith item you need. Okay, this is a bit different from what we have written here. We can ask ChatGPT for some test cases. Yo, I have written a classic knapsack solving program. Can you give me some weights and values and corresponding values, and also the target capacity to test my program? Let's see. Nice. Yep, these are the weights. Okay, give them to me in array format. Okay, just a single thing. These are the weights. Wait, okay, here the expected value is to 220, and in our case, the expected value was 22. These are the weights, so, and we can do something amazing. I this and paste. That is Vim. Vim is pretty cool. And here I inside this, and we will copy this thing and paste. That is pretty cool. And here capacity is 7. Let's see in our hard-coded answer. Okay, so something went wrong. Something went wrong. Expected value is supposed to be 220, but we are outputting 240, which is wrong, which is wrong. So something messed up. Something is wrong. DP weights I, that seems to be right. And then we are iterating for every item, starting from the first item, right? Starting from the first item. How would we get this thing? We would get this thing by using this and this. Yep. But shit, I can use shit. My answer is correct. My answer is correct because I can use this item with a weight of 20 and this item also with a weight of 4. Now total weight is 6. Then I can also add this item with a weight of 1. So 7 is the total weight, and I will get 100, 120, and 20, which is 240. So my answer is correct. Capacity. You shit. Chat GPT is wrong. Your answer is wrong. Means I can choose the items with weights 2, 4, and 1 with a total weight of 7 and get a value of 240. How can ChatGPT's answer be wrong for a thing this simple? That is crazy. That is actually crazy. But okay, ChatGPT can be wrong. Do not blame ChatGPT. ChatGPT just sees whatever is on the internet and yaps about them. Okay, so this seems to be correct. Our algorithm seems to be correct. Now, what we have to do is get to know this thing when we can change this two-dimensional array into a single dimension. That would be actually cool. And go through the rest of this article and at the end do some knapsack problems. Some at coder problems I have not done. I think I have done a few, one or two problem on at coders, but that would be cool. Bookshop. Yep. This optimization is actually cool. This optimization, when you are changing your array from two-dimensional to a single dimension. This is cool because whenever you are trying to find value for f of I, all you need from the previous state is f of I minus 1, and here also in both the cases you only need f of I minus 1. So you only need the last state. You do not need all of the last states which have been till this point. So you can eliminate all of them and only keep track of the last one at this point, which is cool because yesterday on stream I was unable to solve this question because of optimization problems. Coin change. See, I was unable to solve this quite a few times, but then I made the optimization. This thing. I made the optimization and so this is actually pretty small. I made the optimization and used a single dimensional vector, which changed everything. And my code became very optimized and pretty cool. I was at one point using, I can even show some modulus operations so that I would always loop back. Yep, here I was using modulus of a lot of modulus operations so that the two-dimensional array I am using, I would not go past it. I would just keep looping around it and I would not, the size would be expectedly small, but in this case, I'm using a modulus operation a lot and modulus operation is very slow. It is very slow. Addition is fast, multiplication is fast, division is slow and modulus is slow. These two are very slow. That is cool. And ChatGPT does agree. Correct optimal output is 240. Now we want to optimize. How do we optimize? Like, how do we optimize? Okay, we can make this thing one dimensional integers, a vector of integers. And what is going to be the size? The size is going to be weights. Yep, this size seems right. And what we can actually do is remove this whole thing and write from scratch. Writing from scratch is actually pretty good. Knapsack. This will take in a vector of integer weight and a vector of integer values and integer capacity. Writing from scratch is pretty good because I will have to go through every single thing again and again, and that is repetition, and repetition is good for us human brains. Okay, now I need a dynamic single dimensional vector. Call it dp and the size is going to be weight dot size plus 1 Yep, weights dot size plus 1, and for int I equals 0, I less than values or weights dot size and I plus plus, and inside for every weight, j is going to represent weight 1 when my capacity is 1, and j less than equal to capacity. We will go till capacity and j plus plus. So what do I need? I would also have to initialize this thing with some value. Yep, I would also have to initialize this thing with one value, for which do I have to go back? No, I think I do not have to create any external loop instead. Yep, I don't think I have to create any external loop. Instead, I should be able to create some condition here. Yep. Let's say I do create some external loop. Yep, I would like to create some external loop for int I equals 0, no, int j. For the this external loop will go for the first item, this item, through all the possible weights and see if we can put this or not. And essentially, this will initialize this thing, our one-dimensional array vector, to this thing. Let's go. J equals 0 does not make sense, but anyways, when our weight is 0 or weight is 1 and j less than equal to capacity and j plus plus. So if j is greater than or equal to the weights 0, the weight of the first item, then the value here changes. The dp, then dp of for j for the jth weight would be value of this thing, and the value is values 0, the first value. Now we have our data initialized, which is cool. We can start iterating from weight number 1. Now, if j minus weights I, if I remove this ith weight, if this thing is still greater than equal to 0, then dp of j equals maximum. Nope, I also have to fucking initialize this thing to something. Yep. Do I need to initialize this to something? Shit, I think I need two vectors. I would need two vectors because when I am, okay, let's make this less messy. What are you doing? Can I get some insight? Yep, we are going through knapsack problems. We have read a bit of this article on algorithms for competitive programming, the knapsack problem, this thing. Under dynamic programming, we have knapsack article, and we have read this much, and we have implemented till this point, and we are now trying to optimize. And the state in this thing is two-dimensional, and we are trying to change it into one-dimensional because one dimension is better than using a two-dimensional state, because two-dimensional state takes a lot of space, which is not good. So what we need is like this: when we are at some particular item number, items are represented by I. When we are at some particular ith item, and this division is of weights, this is division of weights j, 0 1 2 3 4 5, something like that. Now when I am at some particular block, I need to know all of these values, all of these values. right? So if I'm using the same array, then I cannot rewrite these values because I would be needing them here. So I think what I can do is I can start iterating from this side actually, this side, right? Find the answer for this, put it here because I would be needing all of these values. Then find the answer of this thing, put it here. For this, I would be needing all of these values, and even if I do change this value, I won't need it, so that is good. We can start iterating from the opposite side, which is j equals capacity till j greater than or equal to 0, j minus minus. Right. So we start iterating from this side and we update the rightmost thing, which we will not be needing later. If j minus weights I greater than equal to 0, then, or even before this, even before finding this value, int v equals 0, then v equals maximum of v. We can just put it to something equals 0. 0 is fine. V equals dp of weight. Weight is j minus weight Wi-Fi stream. Weights bracket I. Just put it equal to that thing. If and this is the case when I am using the current value, and when I am, then the value here becomes plus value of the ith item. That is cool. And v equals maximum of current value of v, which either is 0 because of this or is updated because we used it. Either it is equal to that or j. Yeah, j is cool. Here we are checking if we did use this ith item in our sack, and here we are checking when we didn't use this ith item to put in our sack, and that should be cool. That should be cool. We can just return dp of capacity. That looks cool. 21. And we would need some weights, vector and weights, and the weights we can use these ones given to us by ChatGPT for testing. And vector integer values, and the values are just these which were given to us by ChatGPT. Yep, and see out answer is going to be knapsack of weights, comma values, and the target, and our capacity is 7. So expected answer of this thing is 240. Let's see if we get that. Lang plus plus knapsack slash out. 6e is not the right thing. 60 is actually bad. 60 is bad. Yep, 60 is bad. 60 is bad. The actual answer is 240. So we messed up a little bit in our optimization at some point. Let's say we will be looking at the state after every iteration. Let's see that. This is our initial state. Then it always remains 60. Okay, for high R, it is not being up. Of course. Of course. Shit. Of course, it is not being updated. j equals v. To update the current value, I am here creating an integer and that contains the current value, and then I am updating the current value here. Now this should be cool. Lang dot slash out and 240. 240 is the correct thing. And also we are using only one dimension, one dimensional array, which is even cooler than that. What is wrong with this thing? Okay, cool. That is much better. Yep, but two dimensions have more info, right? Yep, we have more info. I want to let you know I am not into coding for work. This is not my cup of tea. I just thought to check upon you. You can. I am from different industry. Totally. That is fine. Where is this rating recorded? What rating? Okay, this. Okay, shit. This is Code Forces. There's this website, this Russian website, where you go and there are contests. Right now, my rating is 1258, which is very, which is bad. And today we have a contest number 1045, and you give contest, and according to your performance, your rating goes up or down. And we have a timer. The contest is going to start in 7 hours and 26 minutes. That is cool. This is competitive programming, which is cool. Knapsack, yep. And yes, 2D arrays do have more information, but the thing is, we do not need all of that information. We only need a certain bit. When I am at a particular row, I only need the information of the row above it to calculate the values in this row. So I do not have to store all of this extra things above. So I can just store a single dimensional vector, which would have the current values. And using that, I can make my new one and forget about this one. That is what we are doing. Single dimensional thing. Yep, this is cool. This is actually cool. This is like F1. You can see, and one more thing is that the fact that is very cool about this is that these are the highest rated players, right? This guy is on number one, a Chinese guy, Jiang Li, 3800 rating, which is cool. And you can go to his profile, go to the contests that he has given, go there and go to this tab, solved, and actually see his submissions, the code that he has written, the actual thing. And I can learn from this. This is pretty cool. Just go there and see what he has written, and I can practice and see what much smarter people who are much smarter than me write, which is very cool. Yep, I live stream regularly around this time. And now knapsacking. Okay, even though we have written some code for the knapsack, it is still not very clear what this thing conceptually is. So the thing that I have come to realize, which is very helpful, is just copy the whole thing, delete it, and write it again from scratch. And we can do that. CSE, this is my boilerplate. And here, function that will return a integer. Function will be called knapsack. Writing a function name is much more difficult than writing the function itself. Weights vector of integer called values and a integer capacity. Yep, capacity. And what do we have here? Yep, we have to create our one-dimensional efficient DP thing, and its size would be capacity plus 1. And then we will iterate through this. Shit, that is crazy. Okay, let's see. Let's see who wins. By the end of this year, I want to reach a rating of 2000. Let's see. Okay. And yes, we would have to go through filling, initializing the whole thing. J starts at 0 while J lower than equal to capacity and J plus plus. If the current J is lower than yeah, if the current J is lower than the current weight, the first weight, then we cannot have its value. So when J is greater than or equal to the current weight that we have, then the value of this particular weight is going to be the value of the first item. And values does not seem good. Yep, value. Now we have initialized our DP, and now we are going to iterate for all the items. Items will start at 1, I lower than weights. Why do I get this well distribution? I lower than weight, not size, and I plus plus. We will iterate through all the weights, and for int j equals 0, we have to start from the end. Yes, we just discussed we have to start from the end. J equals capacity, and j while greater than equal to 0, j minus minus. The weight, we can start with value equals 0, and we can remove a random. What we need is if I use the current thing, then the weight is going to be j minus weight I if I use the current item, and if the weight is still greater than equal to 0, then I can update v to be equal to the best possible weight when I was not using this item. The dp of j minus weight of I, and dp j minus weight of I is the best possible value when the weight was j minus weight I. And what is j minus weight I? J is the current total capacity and weight I is the weight of the current item. If I do use the current item, then the value is going to be equal to the remaining weight, whatever the remaining weight was, plus the value of the current item which I just used, which is value I. And then value is going to be either that thing when I did use this current item, or dp of j. dp of j. dp of j is the best possible value when the total capacity is j. So that is good. And now I can update my dp of j equals v. And why did I have to use this variable v? Because I am changing dpj, and to get the new value of this dpj, I need the value of dpj. That is why I think I can actually avoid using this external variable. Oh, shit, I can actually avoid using this external variable. Shit, yes, I can do that. I can do that. So dp of j equals maximum of this thing and dp of j. That is good. So we now only have a one-line condition. That is cooler. That is much cooler. And now again, return dp of capacity using our whole capacity. Vector of integers called weights. We can use the weights from ChatGPT. Just wondering if you are interested in creating software development projects as well, or just CP. For right now, just CP, software development later, not right now. Right now, I am just trying to get better at competitive programming. And competitive programming seems much harder than anything else because you have to study a lot. And if I can get better at competitive programming, everything else would seem much easier. At least that is my theory. And here we have the weights. Shit, I messed up the weights and values. Anyways, we inside delete, I this paste, go there, paste. Vim is amazing. See out. Answer is going to be knapsack when using not well. Wait, what even was that? While viable distribution. Shit. Weights, values, and capacity is 7. Let's see if that works. That should work. Blank knapsack slash out 240 is the correct answer. So that is good. We can move on to reading more stuff. Which is so we have seen this that we need two-dimensional array, but we do not actually need two-dimensional array. We can make do with one-dimensional array. And this is what we did. Fi is going to be the maximum of Fi or Fi minus W plus V, which is what we did here in this step. dpj equals maximum of dpj minus weight I plus value I, or just whatever the value was of dpj. So that is a big optimization because the number of weights could be very high, and our two-dimensional vector, two-dimensional matrix that we were storing could take a lot of space, which is bad, which is actually bad. That should be executed on descending order of j so far that, yep, uh, yep, we should be descending j. Yeah, we have to move from the biggest j to the lowest. That is what we are doing here. J equals capacity and j keeps decreasing, j minus minus. Yep, so that when we are accessing j, j f j minus wi means this thing, the j minus wi for the previous item and not the current updated item. So that is important. And it is important to understand this transition rule because most of the transitions for knapsack problems are derived in a similar way. Transition. By transition, do they mean transition from 2D to 1D, or transition in the sense how we are updating that transformed, optimized one-dimensional vector? And now implementation. That is very small. That is very small implementation. And yes, the time complexity is going to be shit. Let's see if we can actually remove this loop here. It would be cool. So initially, our whole thing is 0, and we want to put at some places value 0. Think we can just remove this. Shit, yes, we don't have to do this. We can remove this, replace this with 0. Yep, shit, yes. This is good. This is good. This will work. This will definitely work, and we will get 240. 240 is the correct answer. That is very cool. Again, okay, let's ask ChatGPT. Give me some big weights and values to test. Perfect. Let's stress test this thing. Weights are these. Can copy paste our weights. Paste and go back here, paste the values, paste. Yep, and the weight capacity is 35. 35. Okay, and expected answer. I won't spoil the optimal answer here, so you can properly test. Okay, let's compile and run. And answer seems to be 615. Is that correct? My answer is 615. Let's see. Is that correct? Nice. Looks like your solver is chewing through the loot. Let's verify that. So the program nailed it. That is cool. My answer is correct. Okay. Give me bigger data set. All right. That is not very big, but okay. Capacity is this. Yep, we got this. Go there, CI this, paste, CI this, copy, paste, copy this whole thing, paste here, and now our capacity is 50 instead. Let's see what the answer turns out to be. The answer turns out to be 1055. Now, let's see. 1055 question mark. Is that correct? Okay, ChatGPT is thinking. And while ChatGPT is doing that, what we can do is change our state from one dimensional to two dimensions and see the change in the change in performance. You can paste this whole thing and 9 int knapsack 2D. Here, our vector is two-dimensional vector of integer because this performance boost is quite a lot, quite a big thing. Capacity here we will have weight dot size and capacity plus one. Capacity plus one. That is going to be the size. And for everything here, return dp capacity when I'm considering all of the elements, and the number of elements is weight dot size. That is the number of elements. And how do we find the best thing for this thing? dp of i plus 1, and for the current weight, which is j, we can iterate j from 0 while it is, and this thing is going to be equal to maximum when I do use the weight. When I do use the weight, it is going to be dp of I into j minus weights of I, but I have to see if that target weight is legible or not. If j current weight minus, if j current capacity minus weight of the current item greater than equal to 0. If that is the case, then dp of I plus 1 j for the current weight equals dp of I dp of I bracket j minus weight I plus the value of this current item, value I, and then dp of I plus 1. I plus 1. Why are we doing I plus 1? We are doing I plus 1 because I is 0 indexed, and our I in context of dp represents when we are using 0 items, I number of items. So when I is 0, we are using 0 items, and when I is 1, we are using 1 item. So when I is 0, I want to say I'm using 1 item because I equals 0 is used to refer to the 0th element. Here, this thing would be equal to maximum of whatever the current value is, which is either 0 or it got updated because of this thing, j, comma, dp of I, which is the previous row, and here would be j, dp of ij. And again, we can just return this thing. I think that should be cool. That should be cool. We will call this function also 2D. Knapsack 2D with the same values. Okay, let's go. You can say answer 2D, 1D. First, let's compile again, not slash out. 1D was very fast, but 2D is bad. 2D is bad due to some reason. Segmentation fault. When I'm return capacity, yep. Weight size, yes. Capacity, yep. I goes from 0 till weight size minus, yep. Yep, that is cool. J goes from 0 till capacity equal to capacity, and if j minus weight this thing is greater than equal to 0, then dp of this update this thing with weight minus I plus value of I, which is also correct. And in this dpi plus 1, yes, dpi plus 1 also makes sense. J also makes sense. J is correct. dpi plus 1 and the dp of the last state. This should have worked. Yep. And also this thing, when I am considering all of the weights available to me, weights dot size. Okay, sure. Yes, this is bad. This thing. Weight size plus 1. That is going to be the capacity. Blank dot slash out. Okay, this was also fast. This was not that bad, but in larger data sets, it's going to be very bad. Hello. In larger databases, this thing is going to be very bad. And I want ChatGPT to give me very... Okay, my answer was correct. Wait, give me some really big data sets, like with weights equal to weights around 1E5. That would be cool. 1E5. That would actually be cool. No, shit. No, no, no. It is going to be bad. No, 1E5 is too much. 1E5 is too much. 1E3 is cool. Because for 1E5, my weight capacity would also be very big, and I would have a loop. I would have a loop that goes 1E5 times for every... This is the number of items. And if my weight happens to be 100, then I would have to loop for every item 100 times, and that is 10 power 7, which is already bordering with bad. And if my weight capacity is 1000, then we are already at 10 power 8, which is bad. And if the number of items is 10 power 6 and the weight capacity is 1000, then we are messed up, 10 power 9. And we can even see our two-dimensional matrix would have dimensions of 10 power 5 and 10 power 3. This is the number of integers we would have to store. 10 power 9 integers, and one integer takes 4 bytes. We did a little calculation yesterday. Yep, at some point, somewhere, we were doing some calculations, and we have this many integers, and this many bytes is taken by one integer, 4 bytes. So 1,000 integers would take 4 KB into 10 power 6, and yep, 1,000 of those 4 MB, and now the total size would be 4 GB for our two-dimensional array for our matrix. Okay, let's test with this. Paste. Those are the weights. Yep, those are the weights. Now the values. Paste the values, and the target is 1,000. And weight capacity is 20,000. Okay, weight capacity is 20,000. Let's see how much time each of them they take. Okay, that is also pretty much instantaneous because the size of n is not that big. See, it would be really easy to see this in CSES. You can actually solve some knapsack problems. Let's go there at add coders, this problem. Yep, that is what we needed. Knapsack this much, a number of weights and values. Yep, that is cool. We can do that. Yep, your solver nailed it. Okay, that is also correct. Okay, that is cool. Now for this thing, add coders. Where even are we contest CPs, CSES? Go to previous CSES. Nope, add coders DP. Yep, let's do this. This question. K knapsack. CD back, CD add coders, ls CD DP, ls n start new vim, and here we go. Boilerplate, and we actually don't need this because we do not have a number of test cases. One thing has only one test case, right? This is our input format, n, and then the total weight, int n and w, taken n and w, and our vector for weights and values is crazy. Vi, vector of integers, weight and value. For int I equals 0, I less than n, I plus plus. What we have to do is cn weight I into value I. We have the weights and values. We can write our knapsack function that will take this whole thing. We do not have to write an external knapsack function. We can write it right here. We can create a vector of integers called dp of size w plus 1, and now we can start to iterate for int I. Int I represents the number of items that we are considering. I less than yep, less than n, and I plus plus, and internally for we will run a loop for every weight starts from the total weight w, while j is greater than equal to 0 and j minus minus after every loop iteration. Yapology. Okay, and for every particular thing, yes, we can actually do something better here. If j minus the current weight capacity minus weight of ith item is still greater than equal to 0, what we can do is dp for that j is going to be maximum of dp of j, or we go dp j minus weight of this item and plus value of this item. And at the end, what is the output format? That is print the maximum possible sum of the values of items that taro, monotaro, taro. Shit, is it actually monotaro? This is Japanese ad coders. There are n items. Yeah. Okay. See out dp for capacities, I think. Yep, with a new line. Let's test this case, and that is a segmentation fault. That is a segmentation fault. Shit. Okay. If j minus weight in this line, if j minus weight, okay, before that, we have initialized vector 2 equal to total capacity plus 1. That is the size, and that is correct. And before even that, we take in n and w, and the way that we are doing this is correct. Then, okay, yes, we are. Okay, makes sense. Shit, I have to give sizes for these things. Size is going to be n for this, and size is going to be n for this. Yep, my bad. Correct answer. Wrong answer. That is wrong. Okay, maybe because just maybe. Yep, yep, we have to do that. We have to do that. And answer would be actually big. So do I have to take in modulo? I think I would have to take modulo. 189, even though it is not said that I have to take modulo, we would take modulo dpj equals, wait, I don't have to take modulo every time. I have to take modulo only this time here. Modulo this thing and yeah, wait, it is long. It is long. Okay, that is this is correct. This is incorrect since I do not have to take modulo, I guess. I don't have to take modulo. Okay, this thing is correct. This thing is now correct. This thing is also correct. Now I can copy this whole thing and paste this using C++20. Let's see, submit. Yo, I am from Meerut. If yeah, from UP. WJ. Okay, that is correct. That is very cool. That is correct. Answer accepted. AC for all the test cases, which is cool. Can I see the test cases so that I can measure my performance? I've not used this website much. At Coder's Knapsack 2. Okay, what is the caveat here? There are n items 1 2 n Okay, weights W1 to VI. Taro has decided to choose some items N and carry them back home in a knapsack. The capacity of knapsack is W, which means that the sum of the weights of the items taken must be at most W. Find the maximum possible sum of the items Taro takes home. So what is the difference between the last thing and this? Weights are given in the same way. Print the maximum possible sum of the values of the items that Taro takes home. Hmm. What is the difference between the two? I guess in their sizes. Yep, number of weights. Shit. I cannot. A loop that runs 10 to the power 9 times. Yep, that is bad. Yep, not even 10 to the power 9. It is 100 into 10 to the power 9. This is smaller, but shit. This is bad. Let's see and submit the code that we have. This thing, the same thing. That is actually bad. Have the written some time limit 2 seconds. I can store much more data. 1 GB of data. Let's see if this works. I think this won't work because time complexity is very high, very high. It is around 10 to the power 11. Not around, but exactly. Yeah, see, runtime error. We got some runtime error. Wait, runtime error is different from time limit exceeded. Standings, custom, submit clarifications. I cannot even see the tasks. It seems that is fine. Okay. We will read something here which makes our code run very fast. Okay, so now what do we know? We know about knapsack. We know how we can change this two-dimensional array storing data to a single dimension array. So that is a big plus plus. And now we also know about implementation. Now we can go to complete knapsack. Complete knapsack is different from 0-1 knapsack in the sense that in 0-1 knapsack, either you choose a given item or not. In complete knapsack, you either don't choose this current item or you can choose it any number of times. That is complete knapsack. And now we will begin. That I was not even in the center. But before beginning, I would like to go to the washroom and I will be right back. We'll be right back in a minute. And yep. And we can, I guess, convert easily our current program that we have written into a 0-1 knapsack, into a complete knapsack by saying that whatever this current weight is, we can choose it any number of times. If we can do that, that becomes a complete knapsack. I mean, that is complete knapsack by definition. But that is also implementation. But how would we define the table in that sense, this tabulation method? Because we can choose a given item any number of times. So what gives? Yes, we can say the next item is always the same item as the before, as the item no, nope. Okay, sure. There will be some caveats, so we would have to look at this thing. The complete knapsack model is similar to the zero knapsack. The only difference from the zero knapsack is that an item can be selected an unlimited number of times instead of only once. That is complete knapsack. We can refer we can refer to the idea of zero knapsack. We can refer to the idea of zero one knapsack to define the state Fij, the maximum value the knapsack can obtain using the first I items with maximum capacity J. It should be noted that although the state definition is similar to that of zero knapsack, its translation rule is different from that of a zero one knapsack. Okay, I think I've seen this term used twice at this point, translation rule. This must be some generic thing, translation rule. Was this there in Introduction to Dynamic Programming? Nope, it is not here. I am searching for it right here. So yeah, it was introduced at some other place, and translation rule is a generic term, it seems. This thing, translation rule. After we read this, we would look into what translation rule means. Explanation. The trivial approach is for the first I items, enumerate how many times each item is to be taken. The time complexity of this is going to be n square w. N is the number of items, W is the total capacity, and that makes sense that we have to go through all of the weights from 0 till W. So that explains the W here. But why N square? The trivial approach for the first I items enumerate how many times each item is to be taken. That, I guess that makes sense. The time complexity, yes, that makes sense, because for every item I would have to iterate through all of the possible weights and for all of the items. Yep, shit, that makes sense. If I have, let's say, item number 1, 2, 4, due to some reason after 2, 1, 2, 3, and 4, I can do for this item, for this particular item, in this range, I would have to iterate taking this multiple number of times when I have taken this ith item, one item, for some particular number of times, and same for this, and do this for every item, that is n square, and do this at every particular weight, which is bad. If n is 100 and weight is 10/6, then n square is 10 power 4, and if we multiply them, we have 10 power 10, which is bad. This yields the following transition equation and transition rule. Okay, Fij equals maximum of k goes from 0 till infinity. You have to iterate till infinity. Yep. When you are taking this ith item k number of times, and you will get its value k number of times, and you have to do this. Here, k is one of the variables, k is one of the variables, j is another variable, and I is another variable. J goes from 0 to W, I goes from 0 to N, and K goes from 0 to fucking infinity. At the same time, this implies it simplifies into a flat equation. What is a flat equation? Shit. So this is, in a sense, somewhat like summation. We are iterating from 0 till infinity. We can convert this into a flat equation also. Okay. When, yes, this makes sense. this would be for 0 knapsack, and this is the general case for complete knapsack, and this is the case for 0 knapsack. That makes sense. The reason this works is that, wait, it simplifies into a flat equation. This thing itself simplifies into a flat equation. That does not make a lot of sense. Okay, in this case, here I am using this weight some number of times, and I add this here, but I am not going back to the ith thing. And here I am not using this weight, I minus 1, and I am asking what was the best thing when I didn't use this particular item for weight j. But this is typical, this is fine. But this thing is when I have used this current item, but I'm reducing the weight. So I'm going back in our array, and this is our matrix, somewhat like this is our matrix, and I am at a particular place like here, then I am looking at this block and some earlier block at some point, because this says I'm going back in row to the above row, and this says I'm going back in column to the last one of the columns, wi times left. Okay, that I think I can iterate, and I do not increase my I here. Yep. No, shit, I am iterating for W, so that is fine. That is fine. The reason this works is that Fi and J minus Wi has already been updated by this. Fi and Jw minus I has already been updated when I was at that point. If I'm going from J smallest to the biggest, this would work only then. Okay. Okay. Similar to the 0 in knapsack, we can remove the first dimension to optimize the space complexity that is messed up. And we are going from right to left. Okay. Here we are looking at the last thing, and here we are looking at the current thing, the current item number. G minus Wi plus Vi. That is exactly the same code which was written above here. G minus Wi plus Vi. Here also G minus Wi plus Vi. Wait, it is okay. Shit. There is some difference here. There is some optimization here actually. Shit, this is actually cool. This is actually cool. While J is greater than, J represents the current weight, and while the current weight is greater than Wi. That is a good optimization which I would like to steal. While this is J is greater than equal to the current weight I. And if that is true, I can delete all of this. And my phone is running out of battery. It is still running out of battery, which is bad. Now we are good. Or no. Yo, okay. Now we are cool. That is cool. Okay, so there is not much difference between the two. Here we start here and we are going from bottom to up. Zero knapsack. Okay. And then there is multiple knapsack. And then there is binary grouping optimization, monotone queue optimization, and mixed knapsack. Okay, I would like to do some problems on CACS at this point on dynamic programming, removing digits. Let's see what that is. You are given an integer n, and after doing these things, we would get back to our knapsacking. You are given an integer n. On one step, you may subtract one of the digits from the number. How many steps are required to make the number equal to 0? You are given an integer n. On each step, you may subtract one of the digits from the number. What does that mean? 5 steps are required. 5 because 27 is the thing and I can only remove 2 and 7. So I remove 7 a bunch of times. Shit, when I remove 7, the number becomes 20. Okay, that is cool. That is cool. If I have 27, if I remove the take the biggest number, which is 7, and remove that, my number becomes 20. That is one step plus 1. And when I have 20, I can remove 2. My number becomes 18. So plus 1 again. And now when my number is 18, I can remove 8. My number is now 10. So plus 1 again. And when I have 10, I can remove 1. So plus 1 again. And when I have 9, I can remove 9. My number becomes 0 and the answer is 5. Shit. That is a dynamic programming question that I haven't seen. Yep, this is the exact same thing here. We have to return the number of things. And this is cool. This is cool. And this is cool because now I have not seen this kind of question till this point. So this is cool and I have to create some dynamic logic on my own. So what I'm going with is for 27. I think recursion would be better here. I can start with 27 and I can see the answer. What I can remove from 27 would be 7. Yep, 7. And the answer for 27 for answer for any number n would be equal to the answer of f n minus mx plus 1, where mx is the largest digit in this given number. And we would have to, so how much time is this going to take? Let's say time complexity would be n into the number of digits. Number of digits is just log of n. Yeah, and log n. And log n is going to be the time complexity for this thing. And log n. Yep, that is cool. And we can do this. Go to there. Nope, not here. Go to CSES or maybe detach tmux. Start again. Tmux set. Tmux attach target as CSES. CDDP and DP problems. There are some updates and lazy Vim. There always are updates. Yep, CVP, CSE. And what is the way that we are getting the input? We are just getting the input like that. And as we can see that the maximum value that n can have is 10 power 6, which is not very bad. We can run a loop for 10 power 6, 6 into 10 power 6 times. This is not very bad. Well, when 10 power is 6, the maximum digits we can have is 7, 6 zeros and the 1. So this is going to be the time complexity, and that is good. That is handleable. For this, we would need a vector of integers. We'll call it dp or res, response, size n plus 1, and we will start iterating from 0, initially 0. Yep. For int I equals 1, and this is the tabulation method, I less than equal to n, I plus plus. This is the tabulation method, iteration and tabulation, which we were talking about at the start, right here. This is iteration and tabulation method. Bottom up, we start from 0 and we will go up till n, and at the end, we will see out res of n. Standard output, right? For this thing, yep. For this current I need to find the maximum digit in this number. And how do I find the maximum singular digit in this number? Shit, it is actually bad. I do not know of a efficient way to find this maximum digit. Shit, we would have to loop for int x equals 0, x lower than even equal to, no, we can store this. Int mx equals 0 and int I, int t equals I, while t mx equals maximum of mx, or the last digit of t, which is going to be t remainder 10, t remainder 10, and modulus is a very bad operation, but still, and then remove that last digit. So we have the last digit in mx. After that, yeah, the answer for this thing is going to be res I equals res of I minus mx. And I think this will never go lower than 0. This can never go lower than 0. Yep, because this digit that I am subtracting from I is inside I. So this will never go lower than 0. And this should work. Plus 1. Shit. Yep, that is correct. I cannot copy paste in CSES. We have to select the file. Documents, programming, competitive programming, CSES, DP, and here we have this thing which is called minimizing coin, fib, coin combination, dice combination, removing digits. Yep. C++ 20 and submit. Let's see. This should be correct. Yep, that is correct. And we can actually go to the analysis tab and see what the official shit. This is the thing that they are using. Okay, shit. Initially it is infinity, and they are taking the minimum. I don't think you have to take the minimum here, because initially it is 0. I don't. Huh? Okay, let's read the explanation first before judging them, before judging the CSES people. A straightforward dynamic solution to this problem is to iterate through all the digits in a number and choose the one which results in the least total steps. Okay, That makes sense. That makes sense. You are iterating through all the numbers and subtracting every number one by one and choosing the minimum. Mm, And that is why you have to initialize this thing to infinity. Alternative greedy solution. Yes, greedy solution. It turns out that always subtracting the largest digit leads to an optimal solution. So we applied dynamic programming with greedy. So that is much better. And this is what they do. Yep, to find the maximum digit. This seems like to be the way. Copy the number somewhere else. Shit. Wait. Shit, this is cool. This is much better than my solution. Shit, this is much better than my solution because they are not even storing any states. The space complexity is constant. They are not storing anything. Shit. This is so cool. This is better. Okay, well, let's read this. The expression num remainder x gives the last digit of the number, and the digits can be shifted to the right with integer division by 10. This is repeated until the number is 0. Yep, we iterate through all the numbers and dividing them one by one. We also have space complexity equal to n, alternative greedy solution. This makes proof. Yep, it turns out that always subtracting the largest digit leads to an optimal solution. Why? Because you are subtracting the largest digit, right? No, that is not enough. That is actually not enough. This makes for a simpler code, but the proof requires some thought. Let's step n be the minimum number of steps needed to reach 0 when starting from n. We will show that the function is decreasing. Yes, if it is monotonously decreasing, then only making the largest jump makes sense. That is for every positive integer n, it holds that n minus 1 is always either smaller than or equal to n. If the function is non-decreasing in the interval list, then it is always, if the function is non-decreasing from 0 till n minus 1, then it is always optimal to subtract the largest digit from n because the total number of steps will be steps n minus d plus 1, where d is the chosen digit, and if d is as large as possible, then n minus d is going to be as small as possible, and for smaller values, this step function returns a smaller or equal number. So that is cool. Where d is the chosen digit, this would also mean that the greedy strategy is optimal. Yep. The function is indeed non-descending for this whole thing since step 0 equals 0 and step 1 equals 0. Okay, for this range it is non-descending, yes, trivially it is non-descending here. The proof is completed by induction. Okay, we will not read any further. We will not read any further. We will prove this whole thing by ourselves using induction. Induction is one of the best things in mathematics. And induction was not present at the time of Euclid's. So they had to do things like pretty manually, which was bad. At Euclid's time, there was no induction. So they didn't had any notion of representing numbers like this. 1 and 2 would mean a 12. They had no notion of that. They used geometry for their things. So we have a function fn, and we want to prove that it is monotonously increasing, even though I don't know what exactly what monotonous means. Increase, monotonous increase is a monotonically increasing function as is one as the input value increases, the output value either stays the same or increases. So that is good. Okay, so this is monotonously increasing. That is what we want to prove. And we have base cases for this function is monotonously increasing. Let's represent monotonously increasing with this upward arrow in the interval 0 to 1. And now we have to prove using induction for this thing is less than or equal to f of k plus 1. If we can prove this, and we know this, that at the starting from 0 to 1, including these numbers, this function is monotonously increasing in this range, and it is always also increasing for every number, for every two number range. Then we can say for when we choose 1 and 2, it will be increasing, monotonously increasing. Then we can choose 2 and 3, it will be monotonously increasing because of this rule. And then in the range 3 to 4, it will be monotonously increasing, and we can keep repeating this thing for the whole number line beginning at 0. And we can say this thing will be monotonously increasing for whole 0 till infinity. Infinity is not included, by the way. And this for 0, f0 equals 0, and f1 also equals f0 equals 0, and f1 equals 1. You have to remove, subtract 1. Now we have to prove this thing. Why? Okay, either k as the last digit has 9, there are some numbers, and k equals to this number which has a bunch of numbers, digits, and the last digit is 9, or k is like some any generic number lower than 9, let's say 8. And when we add 1 to this thing, we would have at the last thing 9. And if that is the case, then we can just if that is the case, then whatever the greatest number was, the greatest digit was, if we remove that digit in this and in this, we are saying that the answer is going to be same. How do we say that? Because that particular thing would become 0. No, let's try with this thing. Let's try with this thing. When we have 19, let's say, for example, k equals 19 and k plus 1 would be equal to 20. When we have something like this, then here removing 19 would give us 20, and removing 2. Okay, shit, that is what we want to prove. That is what we want to prove. Shit, that is what we want to prove. That is cool. Okay, shit, yes. Here we would have 19. If k has the last digit equal to 9, then removing that last digit, our answer would become 0. The last digit would become equal to 0. And if we increase k by 1, k plus 1, then our answer, the value that we get, is going to be bigger from the value that we would have gotten when k was equal to 19, when k had 9 as its last digit. And we are saying that the answer for this thing, f of this thing 10, is going to be smaller than equal to f of 18. And this actually makes sense because you have to do one more operation here to get this down to 0. So that is why this thing is true when 9 is the last digit, because to get this thing to this, you have to remove 8, and that is one more operation. So therefore, in this case, the value for f of k is going to increase by 1. But when the last digit is not 9, then you could say the last, let's say the largest value is any other value, whatever it is. Whenever you subtract that thing, the last digit that you get here is going to be one lower than the digit that you would get when k plus 1. Or you could say to get them both to make the last digit equal to 0 in both of those things, you only need one operation. Does not matter whatever the last number is in k. Let's say it is 2 and the last digit in k is 2, then the last digit in k plus 1 is going to be 3, and to make both of these equal to 0, you only need one operation. Here you can remove 2, here you can remove 3, and you will get 0. You will get 0 in both the cases. Therefore, f of k will be equal to f of k plus 1. In this case, when k's last digit, we can write this in C++ way, k dot back is not equal to 9, then this thing is true. And therefore, we can say f of n is monotonously increasing. Therefore, keep therefore decreasing n as much as we can, that is using a greedy algorithm, would give us the best possible answer. We want this delta to be as high as possible. This delta should be as high as possible. That would be cool. And this solution that they have given here, this is very elegant because they are not storing any vector state. This is very elegant, and I will copy this shamelessly. While n, what do we do? Int steps initially 0, and at the end cout steps with a new line, of course. And what do we do? Here we find the largest digit and decrease that from n. Int t equals n, and int mx equals 0. While t mx equals maximum of mx, comma, last digit of t and t divided by equal to 10. And steps plus plus and n minus equal to that maximum digit. This is very beautiful, and it is also correct, which makes it even better. And we didn't read their proof. We can greedy proof of correctness. This thing we will show that function is not non-decreasing. That is, for every positive integer, it holds that steps, this thing is, yeah, step n is greater than equal to step n minus 1. If the function is non-decreasing on the interval 0 to n minus 1, that is, it is non-decreasing. Its value either increases or stays the same. Then it is always optimal to subtract the largest digit from n, because the total number of steps will either remain same, or the total number of steps would either remain same. Oh, no, they would increase by 1 always. But for this thing, if d is as large as possible, then the total number of steps either would be same for a smaller d, or would be lower for a larger d, where d is the chosen digit. This would also mean that the greedy strategy is optimal. The function is indeed this thing, non-decreasing for the range 0 and 1. Yep, steps 0 is 0 and steps 1 is 1. Now the proof is completed by induction. Assume that the function is non-decreasing on the interval this. Assume for some number n greater than equal to 2, the induction hypothesis is that this thing is true. And that is what we have supposed to be true. Assume the function is non-decreasing on this interval. And so the function is non-decreasing on the interval this as well. Okay, we have just assumed it to be true. When comparing the digits of n minus 1 and n, notice that the maximum digit of n can be at most 1 greater than n minus 1. Yep, at most greater than, yep. Let d be the maximum digit in n minus 1. Yep, if we are saying that d is the maximum digit in n minus 1, then steps n minus 1 equals steps n minus 1 minus d plus 1 for removing d, and d is the largest digit in n minus 1. And in n, the largest digit can at max be d plus 1. On the other hand, the maximum digit of n is at most d plus 1. So n steps is at least answer for this steps n minus d plus 1 plus 1. Shit, this is the same as this steps n minus d plus 1. Okay, n minus d plus 1 plus 1. That is actually the answer for steps n when we are removing d plus 1. Okay, when our delta is d plus 1, we are removing that from n, and plus 1 for removing d plus 1. It equals to this thing. It is either equal or smaller. This is the same as steps n minus 1 confirming the induction hypothesis. That is cool. And we can submit our more optimized solution here. Now, no files are chosen and removing digits. C++ 20. Cool. Accepted. That is much better. Cool. Cool. And we would like to do some more problems, dynamic programming questions. Grid path 1. Okay. Consider a n by n grid whose squares may have traps. It is not allowed to move to a square with a trap. Okay. Your task is to calculate the number of paths from the number of paths from the upper left square to the lower right square. You can only move right or down. Okay, that is really cool. We will have something like this, and we have to output the number of paths that start from this place and reach this place, and we cannot go to squares which are like this. That is cool. That is cool due to one reason, which is in this book, Competitive Programmers Handbook. If we go here and we go to dynamic programming, and there if we go to paths in a grid, path in a grid, that is the exact question that was asked, which is cool. Not just this, this is, yeah, this is cool. This is cool. There was another question in complete search chapter, which was very much like this thing, basic algorithm for this pruning the search. Yeah, we can prune the search actually. Okay, so first of all, we will write our unoptimized question, grid path 1. Okay, that is why there are two questions, path 1 and path 2. There must be grid path 2. We have grid path 1, where is there is no grid path 2, it seems. Grid path, how do I print this character? This is just capital I, it seems. Grid path. search grid path here, and yep, grid path 2 in counting problems. Okay, grid path 2 is in counting problems, and it is very hard. I think because it requires pruning. No shit, it is a totally different question. Anyways, let's get back to our question. Let's do this grid path. Okay, what do we have? We have first n, which is the dimensions of our grid, and n taken n, and our grid will be a vector of string called grid of size n, and for int I equals 0, I less than n, I plus plus, we will do cn grid I. Yep, can do that. Now, when we have the whole grid, what do we need is we have to iterate from for int x equals 0, x lower than n, and x plus plus, and inside another we will have another loop for int y equals 0, y less than n, and y plus plus. And we would also need delta. Let's define our delta. Delta is just the steps that we can take. So that would be an array of array, or we can say a pair of integers. We'll call it delta. An array of that thing equals, first delta is -1, 0 comma 1, then the next can be 1 comma 0, then the next can be -1 or 0 comma -1, and then -1 comma 0, and this, and we can even say char obs, that is the obstacle is this thing. Now we will iterate through our delta for auto dx delta in x delta y in delta. What we need is int nx, that is new x, equals x plus delta x, and in ny, that is new y, equals y plus delta y. And if they are in range, if nx greater than equal to 0 and nx lower than n, and ny greater than equal to 0 and ny lower than n, if we are still in the range, and also, and grid. Okay, shit, what are we even doing? Yep, we need some initial state that, yep, a vector of int vector integers response size n, comma vector of integers of size n, and response for 0 0, that is going to the first place. There is only one way to be there. If it is already not, if there is an obstacle here, I cannot be there, right? You can only move right or down. Your task is to calculate the number of paths. It is not allowed to move to a square with a trap. Squares have trap. May have traps. After this, there are n lines that describe the digits. Yep, this denotes a trap. And we would also need a modulus. Const in m is 1e9 plus 7. What do we need? Nope, not grid. Yep, grid new x and new y if it is not equal to ops. Only then move there, and therefore it should. This is bad. Shit, I have to change my delta. I can only go back. Yes. If I can go to that place, then number of ways there plus number of ways there. Yeah. So res x y equals plus equals res nx ny. Does that make sense? That seems to make sense. Res xy, it is the sum. Yep. Okay. Res for the current response for the current one equals to the sum on the top one. Number of ways to get to this one above it. That is, if I am at a particular square and there are squares like this, that is when I can do better. I can create the Windows sign better than this. Here, if this is a grid and I am currently at this square, there are only two ways to get to this square, either from this, the square above, or from the square to the left, and therefore the answer for this would be the number of ways to get to this square plus the number of ways to get to this square. And I am iterating from top left from this square, then I go here, then I go here, and yep, I am iterating from top left like this. And then at the end, see out res I, no, res n minus 1 and n minus 1, and I don't just think, I know for a fact that I don't need two-dimensional array. Yep, I don't need a two-dimensional array. I don't need a two-dimensional array. I don't need a two-dimensional array because that makes sense. For int x equals 0, x lower than n, and x plus plus. Now we are going to iterate for every y, int y equals 0 initially, and y lower than n, and y plus plus. What we will see, now we will iterate through delta for auto dx delta x and delta y in delta, and int nx equals x plus dx, and int ny equals y plus dy. If these are in range, nx greater than equal to 0, and nx also lower than n, and ny also greater than equal to 0, and ny also less than n, and that path grid nx and ny isn't equal to obstacle. And if the current path in the grid, if grid if grid x y equals obstacle, then go to the next one, continue. Right, if this is the case, if I can go up or back, then res y equals plus, okay, I have to change things a little bit here. I can even remove this delta. I don't need the delta anymore. If the current thing in the grid is a obstacle, then continue. Otherwise, Otherwise, res y equals plus equals if y, then res y plus equals res y minus 1. Yep, res y. Shit, we cannot do that. We cannot do that. We cannot do that because there are obstacles. Shit, we cannot do that. There are obstacles. Shit, we actually cannot. We cannot use this. Okay, we would need some more elegant way to reduce our space complexity. So let's first of all try to do this in some less elegant way. See out and minus 1. And I think we can somehow reduce the space complexity, but not right now. Right now, we will go some non-elegant way. Dx, and I also removed the delta from here, which was a pair of integers called delta equals minus 1 comma 0 and 0 comma minus 1. Those are the only possible moves that we can make. Dy, no, dx comma dy, we are iterating using that comma delta in our delta, and int nx equals dx plus x, and int ny equals dy plus y. And if they are in range, if nx greater than equal to 0 and nx also lower than n, and ny greater than equal to 0 and ny lower than n, and grid nx ny isn't equal to an obstacle, then response of x y plus equals response of nx ny. That should be correct. Let's see, that is not correct. That is somehow segmentation fault. Because of this, of course, that is a segmentation fault. But int n, that is the correct answer. Okay, and yes, this will mess up. This will mess up. After doing this, you have to do res x y modulus with m. Now we should be cool. Let's see. Grid path, submit. Grid path first. That is a thing. Yep, grid path first. Okay, shit. I think I know what the problem is. If grid 0, 0 equals obstacle, then cout 0, and yep, exit with 1, or return, exit with 0. I will not look at the test case which gave the wrong answer. I'll just submit this and hope that I got the problem. Yep, that was the thing. That was the thing. Right? Yep, here. Either starting square itself was an obstacle, so I couldn't get to the end. So that is cool. Okay, I think we can do a few more questions. And yep, we can do a couple of more questions and then continue our journey on knapsack. Zero knapsack, we have done zero knapsack. Then complete knapsack, we would also have to implement some complete knapsack questions. You are in a bookshop which sells n different books. You know the price and number of pages of each book. You have to decide that the total price of your purchases will be at most X. The total price is X. What is the maximum number of pages you can buy? You buy each. That is knapsack. That is exactly knapsack. Here, value is represented by the number of pages and price represents the weight. Okay, cool. How do we get the input? The first line contains two integers, n and x. N is the number of books and x is the maximum total price. Okay, and the next lines contains, yep, then I have price of each book, then I have number of pages in each book. Okay, cool. That is simply knapsack. CFE, yep, n number of books, and let's call capital P the price, and then a vector for weights, not weights, a vector for price size n and a vector for page price size n, and we will iterate for int I equals 0 I, or we can iterate more elegantly for auto reference xn price cn x and do the same thing here for pages. Now we have the prices and we have the pages, and we will do something better. Vector int n response p plus 1. Our response array is going to be one-dimensional response array from p plus 1, yeah, from 0 till p. So in total we will have p plus 1 elements in our array, and we need to know if our for int I equals I is the first number of books that we are choosing. I starts from, yeah, 0 and I goes till equal to n and I plus plus, and we are going to do this for every page. Int p equals 0 and p lower than equal to capital P and p plus plus. But we have to iterate the other side, the opposite side, while p greater than equal to 0, and here we have p minus minus. And what do we do here? We need to know, we need to look back, yes, above or back. And actually here we can make a little modification. When page I either equal to or greater than page I, if that is the thing, then res for I plus equals res for, not I, what is I? Nope, not for I, for p, number of pages, current number of pages is current number of pages, p minus page price, p is price, p minus price for the ith element, not this exactly, but the maximum of the two values, maximum of this plus plus page I, pages in the ith book or whatever it originally was. That should be cool. See out. Recipe. Recipe. See out. Recipe. Okay. For int I equals 0, I goes till n. I, what does I represent? I represents the first I books. And this is 0 index. So I equals to 0 means the first book, and I equals to 1 means the first two books. And then we are iterating for P. P starts at the maximum price if we are using the first I amount of books, and our maximum cost price starts at P. P is the number of P is the price. If our price starts at the maximum price that we can buy the books for, the first I books for, and we will keep doing this while this maximum price right now is greater than or equal to the page of the current book, which is bad, price of the current book, which is greater than equal to the price of the current book, right? Because we do not want the price to be negative, right? And we do then p minus minus, then price, then the result for p, this current price equals to maximum of whatever value it originally was, or choosing this ith book by removing from the total capacity of our price minus the price of the current book I book, and adding the number of pages to this thing. This should work, and it does. Okay. And do we need some modulus? Nope. This is good enough. Seems to be good enough. No, why would we even need a modulus? Nope, we don't need modulus. We can submit this as it is. Books, removing digits. Nope. We are into bookshops. Submit and accept it. That is cool. What is the analysis? It is just basic dynamic programming question. Knapsack, basic knapsack question. This problem is a type of knapsack problem which can be solved effectively using dynamic programming because of the limits. And this would have given us error actually if we were to use two-dimensional array. Here we are only using one-dimensional array, which is cool. Two-dimensional array would have given us some error, which is bad. Now this problem is a type of knapsack problem. Let total ij denote the maximum total amount of pages obtained by spending at most j money buying only books with indices ranging from 1 to I. Yep, it is just basic knapsack problem with that. Yep, you create a vector, you take in all the values. Yep, basic iteration with tabulation and dynamic programming. References, there are references. Competitive Programmers Handbook, that is the book that they have written. Larkson. Okay, there are other books also that they have recommended. You can go and read this Korean version of the book if you want. There is this Russian version of Guide to Competitive Programming. And Guide to Competitive Programming is a printed book published by Springer. It is based on Competitive Programmer's Handbook, but also discusses more advanced topics. You can buy the book. Should we could buy the book, actually, Guide to Competitive Programming. Okay, that is a cool book. Okay, we can, of course, get this for free from somewhere. And now back to Knapsack. We have written code for zero knapsack, and now for complete knapsack. This is the implementation for complete knapsack somehow. This much is enough. Okay. And to be honest, I do not get this part. How can we convert this thing into this thing very efficiently? The reason this works is that this thing, f of I j minus wi, has already been updated by this. Okay, f of I j minus wi has already been updated by j minus 2 into wi. Hmm. F of I j minus I has already been updated by that, by when our lower limit was smaller. Okay, this makes sense, but you can convert this thing into this thing. There is a bunch of ranges. Okay, either you keep the same amount of things there are, or you use this once and increase the value. You use this once. This is the earlier value, and this is the value right now. You use this once and find the answer. But here we require two things. We require I minus, so we cannot update the values right now. Despite having the same transition rule, the code above is correct. Incorrect for zero knapsack. If observing the code carefully, we see that the current processed item I and the current state Fij, when j is greater than equal to w, Fij will be affected by the smaller values. This is equivalent to being able to put item for int ij. Yes, I is the number of items that we are considering and j is the weight. We start the weight at the current weight, and from that we are going above till the total weight capacity, right? That makes sense. And fj equals fj. Fj is the answer. Okay, fj equals maximum of whatever the current value is of fj, or either we used fj. Okay, that makes sense. We can do that. But why? How can I do this multiple times? Because my value of k has to go from 0 till infinity. So how? Why does this work? Yeah, I will be right back. I have to go to the washroom, and yep, I will be right back in a minute. You. I'm back, and the thing is, we have made quite a progress. Before starting, before starting this, I only knew what knapsack problems are, just the definition, but I didn't know how to solve them. Now we know how to solve 0 1 knapsack. We have done that, and we have also solved some CACS questions, quite a few. We have solved 3 CACS questions, which were not very hard, to be honest. These are and this one seems to be like this is going to be hard because only 36,000 people have been able to solve this. Okay, so in today's stream till now we started from not knowing how to solve a knapsack problem, and till the end, at this point, we have solved, we know quite fairly well, I would say, how to solve a 0 1 knapsack, and not just solve it, but solve it efficiently by changing our state from two-dimensional array, two-dimensional vector, to one dimension. That is very efficient. And also we have some idea about complete knapsack, how you can solve this. Like even though this does not make sense, we can implement it, but just implementing is not really good. We have to know why this works. That would be more important. So we have done that, and we solved some CSVS problems. We wrote some code. We made some diagrams, and it has been 2 hours and 52 minutes. And I would say I would like to go out and take a walk right now. And therefore, this would be the end of today's stream. And thank you for being here.